Hello everyone, my name is Jonas van Pitte and I am a PhD candidate at SEK-CEN, the Belgian Nuclear Research Center. I'm currently in my fourth and final year of my PhD. My research focuses on monitoring uninstrumented irradiation capsules. Those are irradiation rigs without electrical connectors. These have the advantage that they are less complicated, can be assembled relatively easily, and are less expensive compared to their instrumented brothers. Today I want to share with you my findings on a particular area of my research that deals with neutron flux monitoring. It is the use of nanocoatings as activation dosimeters. In the field of irradiation chemistry and irradiation damage to solids, the neutron energy distribution and the neutron flux are essential parameters to evaluate the result from neutron irradiations. This can be a challenge because in material test reactors the power level can change. You also have different experimental assemblies, control rod positions and local burn-up. Those can all perturb the local neutron flux density. Reactor dosimetry is the experimental field that deals with characterizing the neutron fields that were present during irradiation. One way to measure different neutron flux levels is with activation foils. This involves the exposure of a probe to the neutron field of interest. The exposure causes neutron capture and transmutation reactions in the material of the probe. Some of the reaction products will be unstable and decay by emitting gamma rays that can be detected. The measured activity of these products depends on the composition, the reaction cross-section and the neutron field that the probe was exposed to. Therefore, when we know the foil data, it is possible to deduce information about the neutron flux and spectrum after irradiation. As I just said, the activation dosimeters are retrieved at the end of the irradiation. They are therefore integrating detectors and give you the total accumulated neutron fluence. It is therefore not possible to use an activation foil to obtain information about any time variation of neutron flux that might have occurred during irradiation. This is a disadvantage. However, their low cost, small size, and the absence of electrical connectors are clear advantages. For this reason, they are the most widely used experimental technique to determine steady-state neutron fluxes in reactor cores. Some materials that are frequently used to detect the thermal and epithermal neutron flux are cobalt and silver. I will show you here the chance that an interaction will occur in function of the neutron energy for cobalt. So you see the cross-section, that is the interaction chance, and the neutron energy. What stands out in this graph is that you can see some clear peaks in the center. This is the resonance energy of neutrons. There you have some very characteristic peaks where there is an extremely large chance that an interaction will occur. These resonances have a negative impact on our activation foil, because the large interaction cross-section causes the so-called self-shielding effect. That means the neutron flux is artificially reduced in the inner region of the foil. The flux is reduced because there are lots of interaction in the outer regions of the foil, whereby less neutrons are able to reach the inner regions of the foil. If we then would try to deduce the neutron fluence from the activity, we would underestimate the actual neutron fluence. It is possible to correct for the self-shielding effect with appropriate correction factors. But these can be very difficult to calculate, and they can still have significant uncertainty. Therefore, experimenters prefer to avoid the use of these correction factors. How they do it is by diluting or using an aluminium alloy of these materials that have large interaction cross-sections, such as cobalt and silver. These aluminium alloys are normally available at typical concentrations of 0.01, 0.1 and 1 weight percentage in a 0.1 mm aluminium foil. These alloys are made by a complex levitation melting process, and this can only be done in small batches at a time. Currently in Europe, we have a shortage of these type of cobalt and silver aluminium alloys. Due to the complexity of the process and the certification that has to be done by different nuclear laboratories, it is expected these materials will not be on the market for another 2 to 3 years. This is a problem. And to make up for this shortage, we have investigated a different approach. What if we make our activationable material so thin that self-shielding does not play a role anymore? The common weight percentages that I just mentioned correspond to coatings of cobalt and silver in the range between 1 and a couple of hundred nanometers. The use of nanocoatings yields two important advantages. First, it is possible to tailor the nanocoating to the experimental needs, to give you an optimal result. Now you have more flexible control over the amount of activationable material because you can control the thickness of a coating. This in contrast to selecting one of the available alloys that would be 0.01, 0.1 or 1 weight percentage. Second, you can deposit multiple layers on top of each other, and this allows to decrease the number of post-irradiation gamma spectroscopy measurements that are necessary. I would refer to such a dosimeter where multiple layers are stacked on top of each other as a multi-element dosimeter. In this work, we've made these nanocoatings with a process called physical vapor deposition. We collaborated with Ghent University and used an experimental setup that you can see here. It is essentially a large vacuum chamber where you have a source material that is the target and your substrate material that is the carrier which you want to be coated. Our source material would be in our case cobalt or silver, and our target is, for example, an aluminium foil. We generate a plasma in this vacuum chamber at the target. In a traditional glow discharge, you would have too much recombination of electrons, and therefore we confine the plasma with magnets. That way the electrons experience a Lorentz force and make orbital motions. Then we introduce argon in this vacuum chamber, and the argon atoms collide with the electrons and get ionized. Then these ions are accelerated towards the target and atomic size particles break free from the target. These in turn are then projected onto the substrate where they generate a solid thin film. If you want to use these nanocoatings to determine the neutron flux, it is crucial that we know exactly how many atoms of activationable material there are in our nanocoatings. Now, there are several ways to achieve this, but by far the easiest is to just co-irradiate your foil together with a standard reference aluminium alloy. Why? Now we know the number of atoms that there are in the aluminium alloy because we can weigh such a type of dosimeter. We can also measure the activity of the reference, and we can measure the activity of the nanocoating. So now we can do some sort of calibration to deduce how many atoms there are in the nanocoating. Ideally, we want to apply a large coating to a carrier foil and then co-irradiate a small piece of this foil with a reference aluminium alloy, and this should be able to help us to understand how many atoms per square centimeter there are in the nanocoating. Now, to be able to do such a calibration, there is a condition. That is, your nanocoating has to be very homogeneous, otherwise it doesn't work. To check this, we have extracted several dosimeters from a coated foil. Then we determined the number of atoms by co-irradiation with standards, and this allowed us to evaluate the homogeneity through the spread in the number of atoms of these extracted dosimeters from the coating. Let's take a closer look at how we can determine the number of atoms. The equation you see here depends on the activity of the coating, the activity of the reference, and the number of atoms in the reference, as I have mentioned earlier. It is possible to rewrite this expression in terms of experimentally observable parameters. Because we take the ratio of two activities that were determined on the same gamma spectrometer, we are able to eliminate a lot of factors. And the only experimental observable parameters that remain are the net peak area and the measurement time. The number of atoms in the reference dosimeter are determined by weighing it. Therefore, this term depends on the molar mass, the isotope mass fraction, the mass concentration of the activationable element in aluminium, and the Avogadro number. There is some uncertainty included in these terms. You have the net peak area, you have the measurement time, the mass concentration of the activationable element. If we now look at the homogeneity, or the spread in the number of atoms, only those contributions to the uncertainty that are random will remain. If there would be some kind of systematic uncertainty, all the results would be slightly higher or slightly lower, but we would not observe them in terms of the spread or the homogeneity in the number of atoms. The result for this experiment was that we had an uncertainty of this method of about 0.7%. That is the 1 sigma standard deviation uncertainty inherent to this method of performing a calibration. This will be a minimum threshold that we use to compare the spread in the number of atoms to. If we have reached it, it means that our nanocoating has a good homogeneity. Now for our irradiation experiment, we have selected Belgian reactor 1. That is a reactor that is made up of a matrix of graphite blocks. And in these blocks there are holes where the fuel rods are inserted. It has a cylindrical reactor core of 4.7 meter diameter and a length of 4.9 meter. This large reactor is air-cooled and its power is limited to 700 kilowatts. It is an ideal tool for this work as we wanted a homogeneous neutron flux in a small region of 20 centimeters by 10 centimeters. This homogeneous flux allowed us to irradiate a set of dosimeters in a region where there is no influence from local flux variation, and standards and nanocoatings can be compared one to another. This was also experimentally verified through the activity of the dosimeters. In the first irradiation, we varied two parameters. The thickness, where we selected 100, 110, 120 and 130 nanometers, but also the carrier on which the coating is applied, a nickel and an aluminium foil, of which the nickel is actually a dosimeter on itself. The dimension of these foils were 5 centimeters by 12 centimeters, which was sort of targeted for the experimental physical vapor deposition assembly that we used. We also combined identical layers of cobalt and silver on each carrier, and an additional protective 100 nanometer aluminium layer. When these coatings were applied, the foils were transported from Ghent to SEKCN, where these dosimeters were punched from the foils. This was done with a solid metal cylindrical punch that pierced 5 8mm diameter dosimeters from each foil. From the nickel foil, 10 dosimeters were selected, which then in turn were separated in two sets of 5. The punched dosimeters were wrapped in a plastic matrix configuration together with the standard reference dosimeters. The configuration is now shown. The standards are shown in bold, whereas the nanocoatings are shown in italics. The carriers are listed as well as the thickness of the coatings. For example, here it says we have an aluminium with 100. That means we used an aluminium carrier and applied a coating of 100 nanometer cobalt and an identical one of 100 nanometer silver to this dosimeter. For each of these conditions, there were 5 dosimeters and we grouped them in the same row. After the irradiation, we determined the average activity per atom of the standards, and this allowed us to determine the number of atoms of each dosimeter in the nanocoating. To investigate the homogeneity, we made a summary of the dosimeters in each row, so those are the dosimeters that share the same conditions. Then we could make a row-by-row comparison of the spread in the number of atoms. This is shown in this graph. You can see on the x-axis the carrier, which is a nickel or an aluminium, and then the thickness of the cobalt and silver layer. For example, 100 means 2 layers of 100 nanometers. The colors, so cobalt is shown in blue and silver is shown in orange. Now you see here a box plot that shows you the minimum number of atoms that we observed, the maximum, the first quartile, the third quartile, and also the median. We can clearly see that there is a linear trend in the number of atoms for the layers where we varied the thickness. So this shows the flexibility and how we can control the number of atoms in these layers. Now, in the nickel dosimeters that were punched from the same foil, we do see a little bit of a difference in the distribution, where the first one seems to have a larger distribution compared to the second one. Also for aluminium, the 100 nanometer distribution shows quite a broad distribution. Now, to investigate the homogeneity of the coatings more quantitatively, I have also shown the spread in the number of atoms, or the 1 sigma standard deviation of the average that we determined. So this is this graph, and again on the x-axis you can see the carrier and the coating thickness, so the same thickness for cobalt and for silver, and again cobalt in blue and silver in orange. So on the y-axis you now see the 1 sigma standard deviation. And now it is clear that for nickel there is quite a big difference between the two sets that were irradiated. In aluminium 100, it is also significant that we have a 4% standard deviation. This is completely unacceptable for any kind of calibration that we want to do. For reference, I have also added a dashed line that shows you the 0.7 uncertainty of the method that I have used. Now, what is the cause of these large deviations? Why do we observe such a big difference between these different sets of dosimeters? Now, after irradiation, we performed a microscopic analysis on these specimens, and these showed delamination of the nanocoating from the carrier. After some weeks, we even saw residue and part of the coatings that peeled off in the plastic wraps we used to transport these samples. We argue that when the dosimeters were punched, the metal cylinder actually damages the layer by the contact with the coating. So it is clear we have a structural problem with our coatings. In physical vapor deposition, it is common practice to add some sort of adhesion layer to relieve stresses between the coating and the carrier. Therefore, we made new coated foils and added a 5 nanometer titanium adhesion layer. In addition, we also investigated different ways to punch the dosimeters from the coated foil. That is, on top of the layer, through the carrier, and pre-punched. In this figure you can see we have added in the second irradiation a green titanium layer. We also added an aluminium protective layer again, and the black arrow shows you where the punching is done. Note that pre-punched means that we first punched the carrier and then applied the coating afterwards. This is somewhat less practical as we lose some flexibility. You also have to know the size of your dosimeter beforehand, and you can only make smaller batches. So it's not really suitable for any kind of commercial depositions. So we have repeated the irradiation in Belgian reactor 1. You can see the standard dosimeters are again shown in bold. Whereas we also have pre-punched dosimeters, dosimeters that were punched on the surface of the carrier, and dosimeters that were punched on the nanocoatings themselves. This is a little bit of a smaller matrix, but this does not matter as the flux profile is flat in this region of the reactor. Now we can again determine the number of atoms of each dosimeter by comparing them with the standard dosimeters. We repeated the analysis of the first irradiation by determining the distribution of the number of atoms. This you can see here. On the x-axis you see the different punching conditions. And again, the results for cobalt are shown in blue and for silver in orange. The box plot shows you the minimum and the maximum of the number of atoms distribution, as well as the first and the third quartile. It is immediately clear that the distribution is a lot smaller compared to the first irradiation. However, there is now a small difference in the total number of deposited atoms between the coated foil, the dosimeters that were punched from with the different punching methods were extracted from the same foil, and the pre-punched dosimeters. This is because there are slight deviations that can be expected due to the experimental nature of the physical vapor deposition setup that we used. For larger quantities, state-of-the-art physical vapor deposition setups offer increased repeatability. There is also a clear positive effect of the titanium interlayer. But to make a more quantitative argument, I will now compare the standard deviations. Here again on the x-axis you can see the different punching methods, and the results for cobalt are in blue and for silver in orange. On the y-axis you see the 1 sigma standard deviation. The dashed line shows you the inherent uncertainty of the method, which, as you might remember, is 0.7%. It is clear that all the irradiated sets show a spread similar in magnitude to the uncertainty of the method. Thus, this indicates a good homogeneity of our coatings. However, there still seems to be a small negative effect when the metal punch is in contact with the nanocoatings, compared to when the dosimeters are extracted through the back of the foil. To conclude, we have tested whether cobalt and silver nanocoatings that were deposited with physical vapor deposition can serve as activation dosimeters. We determined the number of atoms in a nanocoating through co-irradiation with standard aluminium alloys of cobalt and silver. The flexibility of physical vapor deposition was demonstrated through the deposition of layers with a varying thickness. We have made cobalt and silver nanocoatings with a good structural integrity and a homogeneity. However, this could only be done when we included a titanium adhesion layer. I'm very excited of this work as it helps to make up for the current shortage of cobalt and silver aluminium alloys. But even more promising is the use of other materials such as niobium. This is an interesting material for reactor dosimetry because its half-life is suitable for longer irradiation, and in addition, its energy response is similar to the damage response function of iron. Currently, niobium activation dosimeters are processed by dissolving them in hydrogen fluoride, and then measuring the activity of a deposit. This is time-consuming and dangerous. Also, niobium can become brittle in longer neutron irradiations. Nanocoatings have the potential to solve some of these challenges that are associated with niobium activation dosimetry. And niobium nanocoatings is the topic of ongoing research at SEK-CEN. Now, finally, the only thing that remains for me is to thank you for your attention. I also want to thank ENEN for this amazing opportunity for me to be able to share my research with you today. If you have any questions, do not hesitate to ask them to me. or alternatively, send me an email to one of these channels.